I want to talk a bit what I achieved with BMX7, the successor of BMX6, and what challenge I think can be solved with this protocol that cannot be with any other protocol. Is this? Okay, it's not so relevant. BMX, what is this? Why? Closer? Okay, in general, for those not knowing it, BMX is an evolution of Batman. It started with Batman Experimental, that's where the letters come from. Then some years ago in Italy, I think it was, on the Battlemesh, I made the first experiment with BMX6, so the next successor, and now we have BMX7, which integrates which continues a bit the concept started in BMX6. BMX6, the main new thing was that nodes and what a node is isolated a bit from, in Batman we had like put everything in routing updates or OGM messages, so they could have become very long and kind of limited if you have like many announced networks, and BMX6 started to isolate these kind of static information. For example, interface addresses or announced networks usually don't change, so you don't have to retransmit them with every routing update, which ends up in the same end device anyway. So it isolates these informations and properties a bit into a description, and from then on, once the description is known and populated across the network, this description is referenced just with its hash. So for example, a routing update, which must reference usually to all the networks and end addresses that it's representing, can now just use the hash of this description and reference to all these details. And in BMX7, I continued this concept. Now that I have a description and isolated such things, I could add more stuff to the description, like a signature, for example, and a public and private key. And this way, now I can identify nodes reliable, because I can verify the authenticity and the signature of the description. I can authenticate identities. I can give cryptographically generated addresses to nodes, and this way have a proof of ownership, so that a node cannot simply claim to have an address that is already given to somebody else. He's not able to create this cryptographically generated address. These are concepts also now from CGDNS and GNU-net. But BMX claims to be much more lightweight and well, and working for embedded devices, and it has been made for wireless small devices. And in addition, it aims to give you a secure routing by securing your routes against untrusted nodes, and this while not messing up with these security concerns and decisions from other nodes, so that you have no interference between different security ideas and assumptions in your network. Another thing I was working on recently, but I'm not going to cover this in this talk, is about a new routing metric that I implemented and want to test here during the battle, which is capacity and interference aware. And the idea is that in the end it gives you as a metric value what you see to all the distant nodes, something that is similar to what you can expect from the end-to-end TCP throughput, so that you have a value which is somehow touchable. Now we always have ETX or some values that you 100%, is it good or not? You don't know if throughput is very high or low, just that it's something better perhaps than another value which is just 99. Okay, but this is just a side note. So coming to my main, what I found most interesting here with this new concept is the secure routing that I claim to provide. Let's have a look at private and open networks. Now, we all come from these open networks, and we have forgotten a bit the security that we have with private networks. If you consider a group of friends whose main priority is to have a functioning network, like we have here, for example, we have 4 nodes, they living in separate places of a city, and they want to have a functioning networks. So what they do, they set up some devices and set up some links and run any routing protocol, And because they have no doubts between themselves, they are all friends, they know each other, they don't care about attacks from inside, and to protect again all the text from the outside world, they just encrypt all these links so that they have a kind of security on these links and can be sure that the routing protocol is not disturbed or interrupted. Of course, there can be other groups of friends, like these yellow nodes, for example. They do the same. They set up some links between them, which are encrypted. Of course, they use their own different encryption key. So what you end up with is, are in fact, two networks, which might be physically connected because you have physical links, but logically you cannot use them. You have two networks. And so it goes on. Maybe another group appears with another group of friends. They have their own network, physically connected, but not usable. In the end, you have a bunch of closed networks. There's no collaboration between these networks, and you cannot benefit from each other. And also some individual nodes, like these green ones, for example, they don't have anything from the whole scenario. They are just isolated. They cannot communicate with each other because they can physically connect to different networks, and also there are physical existing end-to-end passes. But they cannot access the routing layer to establish end-to-end routes. And this is what BMX aims to solve. Aims to solve. What it can provide is that all individuals are allowed to use existing physical infrastructure. But so in this case, for example, these green nodes are able to use the routing infrastructure or the physical links which exist end-to-end to the other end of the network, but at the same side ensure that groups of nodes which want to be not disturbed and want to ensure that nobody else can interfere into their routing decisions and their established paths are not affected. So discussing this a bit more general, you want to secure and open and decentralized networks. Personally, I haven't really seen this before. The common problem is usually that a single node, if it's allowed to interoperate with you, then it can attack all of you, even if it's very remote or far away. There are typically two ways to do this, on the control plane or on the data plane. The control plane I consider more dangerous because here you must not be in an existing path. You can do it even from a remote position. For example, one attack that I just tried with my protocol which is distance vector based. If you manipulate the sequence number of your routing updates just by publishing a routing update with an ID of somebody you want to attack, but just with an increased sequence number, you immediately attract all other routes to you, which should guide packets to the node that you are attacking. So these are the common problems, and the common solutions are, at least especially for ISPs, you just exclude all unreliable nodes. What they do is then they have like a centralized administration of their own routers, and these approaches are supported also by existing mesh routing protocols like Secure OLSR or Babel HMAC, or OSPF also has such features. Sorry, but okay, but this is not what we want, because we want an open solution. And when you try to approach this, you quickly recognize that trust and reliability assessments in the community networks are pretty hard. On the one hand, we have these distributed administration. It's not like with an ISP who have a centralized administration of their own routers. And you can have subversive attacks, like let's say selective dropping. Maybe everybody thinks from an attacker, a blunt node just dropping all traffic, or always trying to attack a remote node, so this is easily spottable, and then he might be easily isolated from the rest of the folks. But if you have just some selective dropping, or maybe it's just about concerns that somebody attacks you casually, or just eavesdrops your traffic, then you will probably have lots of controversy who's trustable and who's not. For example, a community might have the offer, from big companies to support the community networks with lots of hardware, but there might be people in the community who do not want that because they want to remain independent from these companies, or they have concerns that these companies just sell the data that they get from the eavesdropping. So, in my opinion, this trust is not a binary decision, but a controversial policy discussion, whatever. And yeah, I forget. Okay, the challenges that we have here, you always have to balance, or what you typically do, you balance between the openness of your network and the security of your network. If you opt towards openness, then you exclude all nodes that have proven to be malicious. But this way, I mean, who proves to be malicious, he probably raised a very stupid attack. And anyway, how can you prove it? That somebody is listening your traffic or selectively dropping your packets from time to time. In the end, you will probably have very few nodes excluded, like in this scenario, you have many nodes. The red node is an identified attacker, so he's excluded, but potential attackers remain, like let's say these yellow nodes. I call them eavesdropping nodes because they just listen to traffic and you cannot spot them. You have them, they remain inside. Or the selective dropper, which I marked violet here. If you opt for openness and you try to find a consensus, so you include everybody unless he has proven to be malicious, you end up in the end with a network which is not secure. And you can opt for the other direction towards security. So you exclude all questionable nodes. Then what is questionable? Somebody who's anonymous or somebody who's just very enthusiastic and it's not clear what his intention is to join the network at all, or kids because they are not reliable and not responsible for their actions. Companies, whatever, even what about competing companies? You may just say, no, this company cannot join because he's my competitor. So you can opt for this, but then your network in the end is not open anymore. And what will probably happen is what we've seen before, that you have lots of partitioning because people create their own networks. Like we have in this example a bit where we have networks here physically connected to other networks, but not logically. Yeah, the complexity is to find a consensus between these two directions. And yeah, the other problem is that finding such a consensus hardly scales, because the bigger your network and your community becomes, the harder it will be to find a consensus who's trustable and who's not. One approach that it exists is to have multiple topologies. And then you say, okay, I have one topology for these kinds of nodes that are considered trustable by this agency, whatever. And you have another set of nodes which are considered trustable by everybody or by nobody. But what I think is the problem remains. You must decide how many virtual topologies do you want to support. Who decides on who's in which topology and how to find the consensus here. And also the questions remain, what is secure in the end and what not. In fact, a common or often suggestion I hear is to have exactly two topologies, one with the core nodes, which are considered to be secure, and then one which is open to everybody. And then people say, now we have a secure and an open network. But the truth is you have two networks, one which is open but insecure, and you have a completely separate network which is secure but not open anymore, it's closed. You cannot simply join it as somebody who is not known or not well known to the community. The interesting thing is all these question marks, they kind of disappear if you have as many topologies as you have participants. Because if you have just for every administrator or for everybody who wants a node, he can have his own topology, then it's the question how many disappears, because you have one for all. The next thing is who decides, that also disappears. It just the person decides for whom this topology is made and decide. You also don't need consensus anymore because everybody can decide on his own without interfering with the others. And the security is then tailored by these admins or tailored by the individuals. So he can say, individually decide these nodes are trustable from my perspective and these not. And regarding the overhead, this I will come back to this later, but that's also the result of my efforts. And we will see that it works in the networks that we are used to. So what I think is a bit, it's like in public transportation networks where this freedom of choice is natural. You can every morning decide if you use a train or walk on foot. Or the infrastructure is there physically, but you must not use it. And it's so in fact there is a virtual topology for every user of the public infrastructure because he can make his own decision and he doesn't interfere with the decisions of the others. So regarding the protocol overview, I'm not going too much into the details. There are many slides, especially for the internals. Okay, the protocol that I developed and which is integrated in BMX7 now, I called it SamTour for securely and trusted multi-topology routing. And it gives security against non-trusted nodes by logic exclusion. That, as I said, topology is just a subset of a physical topology. A virtual topology is just a subset of a physical topology. And the objectives here are that yeah, so yeah, these slides some of these pages are not from today, but from another talk, and this is a bit full. So I have to make one step backwards. Yeah, the first sentence, mutually trusted and cooperative nodes cannot be attacked by externals, is what we had in the first slides with our friends. We had these 4 friends which created their own network. They mutually trust each other, and the objective is that these friends cannot be attacked by externals. The other thing is, of course, that you have no defense against attacks that are coming from trusted nodes. Like in this example we had in the beginning, we had these 4 friends. I'm only protecting against attacks from people which do not belong to this friend group. So, but if one of your friends is then attacking you, somebody that you individually trust, the problem remains. And regarding openness and decentralization, the objective is that new nodes, even if they are unknown, are generally supported according to their trust decisions. That the trust decisions of them define their own virtual topology, and that you can have unrestricted combinations of these trust sets, and these virtual topologies can be overlapping, and it's always an individual decision, and that there's no central registry or orchestration. All these decisions are orchestrated by the individuals. The other last objective is that in the end, the scalability of these protocols should be within the capacities of the nodes that we are using today in our mesh networks. So it should not be a monster big thing which only runs on a 4-core desktop, whatever, but in a better device. And the basic approach is that individual nodes can dictate essentially to all other nodes, these are my trusted nodes, and any traffic which is dedicated to me should only be routed via this list of other trusted nodes. And in the other way, in the other direction, they say, because routing updates are used to propagate and establish end-to-end passes, that only routing updates are considered as valid if they have been received via one of my trusted nodes. One assumption I'm doing is that the owner of a traffic, of traffic in general, and the owner of a routing update is given by the IP address, which is a cryptographically generated address, and the owner of traffic particularly is the person who, or the node which has this IP address in the destination field. So it doesn't matter where a packet is coming from, the destination has the power to control where it can be routed and where it should not be routed. Another thing I want to mention, the way how trust is assessed is out of scope here. I mean, the thing is, I'm providing like tools to enforce decisions, but I'm not providing the tools to make the decisions or to find to identify who's trustable or who's not. This is somehow left to the individuals, but it can be other, let's say, applications can later help to solve these problems. Or common approaches, like you have a public key server with a network of trust, and you just import these trusts that is published there. Or you have a reputation system, but that's another story. It's just, with my protocol, I'm providing the tool to enforce an already existing set of trust or of existing set of decisions. Let's continue. I have now protocol messages which go a bit more into details. I will skip about the most of them, just to give you an idea about this description. Typically in a distance vector protocol, you have a routing update, and this contains a destination address, like 1234, sequence number, and a path metric value. And what I'm doing now, I mentioned this in the beginning, I replace this IP address, which has been used earlier, with the hash of the description. The description is propagated before, just flooded, and it contains more details about this destination node, or the originator of this routing update, like its primary address, the trust set that I was mentioning, a list of other trusted nodes, a public key, and essentially the hash of this public key is just its identity, and a signature, which of course must match this public key. So this can simply be flooded, and if you now know the identity of somebody, you can simply catch his description, you can validate it because it has a signature, and you can see if this ID matches the signature. And you can understand also the rest of these characteristics or properties that are described. Then once this is, okay, I'm not going into the details here, it's just that you can reference other content from one description, and it tells a bit how these messages are flooded and resolved and propagate. Let's come a bit to integration and what I did to validate these concepts. From the integration, it's on the way. There are some first integrations of this in QMP and also in LibreMesh, which have been mentioned yesterday. Here's just a screenshot from the web interface in the experimental QMP branch, which shows like this primary address, this crypto address, the short identity, a host name, it's also part of the description, so it's already known. Here is a metric which is expected, or which has established end-to-end to this node, and the neighbor. And here you have kind of a table, just given with acronyms, but the bigger S stands for supporting, I support this node. The bigger T stands for I trust this node. And the small t identifies if this node trusts me. So here, because for the beginning we haven't propagated different trust sets, and this A simply means I trust all, I support all. So it's not actually testing in real life yet how these different trust sets and maybe also problems, because some paths that you might exist don't exist logically for you, has not been tested in the real integrations, but the infrastructure is there and the web interface is able to summarize these sets. What I did to validate it regarding its performance and scalability, all this has been implemented on top of BMX6. And yeah, to test it, I used a real embedded device, one of these 10 euro routers we know from some years ago already. And I stressed this real device with protocol traffic that I generated from a virtual network. But so the network was looked essentially like this. It was a grid network with up to 200 nodes. I changed the number of nodes by just adding more rows here to this virtual grid. And I changed the number of links that exist to my real device by just adding more links to the emulated network. So here, in fact, in all of these devices, although they are emulated, there was a real protocol instance running. And in the real device, there was OpenWRT running with my real implementation. And then I played a bit with the parameters that I have. And here you see, for example, the impact of the network size. In the graph, just to space problems, I summarized several outputs. Interesting, of course, is the CPU and what the node itself is sending. I increased the number of nodes from something around 4, I think, or maybe no 20 or 10 to 180, maybe, I think, 50, 60, yeah, 180 nodes. And you see the CPU was barely increasing. Of course, the number of transmitted bits or transmitted data was increasing, but it remained linear. And it clearly remained within a scale that if you compare it with other protocols, it's reasonable. It doesn't exhaust or exceed what is possible with these devices. Also memory and these things, it all increased rather linearly. Despite we are having asymmetric cryptography involved, and we are signing routing updates hop by hop, also asymmetrically, and we are signing descriptions also asymmetrically. Then I also looked at the density by adding the number of, increasing the number of links that I had to this real device, here from 4 to 20. You can see similar results. Of course, here the received traffic increases most because, of course, with every new neighbor I get, I receive more data from him. So this is the most increasing dimension or outcome, but same with others. You can see that memory is essentially not affected by the increasing number of links, which makes sense. The node description, which consumes most of the memory, is known anyway. The only thing that has to be maintained in advance, or in addition to having an additional link, is the state of the links itself and the packet loss and so on. Yes, I tried this with different key strengths. Here I changed the key strengths of the RSI key used for packet signing from 512 to a higher value, like this must be something like 1,500. Well, they are not so much valid possible settings for RSA, like 512, some between 1024 is common. Today, 2048 is suggested for long-term or relatively long-term security. What I have dropped a bit earlier is I'm using two different keys for the node description and for the packet packets which are exchanged between neighboring nodes. And the second key, which I'm using for exchange of packets between neighboring nodes, is a weaker key. But the thing is, I'm replacing it very often. That's what in my default implementation, or in these experiments, I've used by default RSA 896, which, by the way, hasn't been at least cracked during these RSA challenges, which are not really open anymore, but which are still public. But I'm replacing this key by default every hour. So I assume that although this is a weak key, which cannot be assumed to be secure for the next years, I assume it's secure for the next hour, then I'm replacing it anyway. And for the primary key, which is used for the description, I've even used RSA 3072, which can be considered secure for many years from now on, from today, knowledge about cryptography. Okay, here I've played with this key strengths for the packet keys. Here I've played with the frequency with which nodes are updating their description. A node can change its description, for example, by adding new interfaces or changing its trust set, because it says, okay, now I know this guy better, I allow him to route my traffic. Whenever such things happen, such kind of reconfigurations of a node, it's just a description update. And of course, if many nodes are doing this, you have to verify the descriptions of all these nodes on the fly, and it increases the load for every node. And indeed, this shows a bit a bottleneck. If you have massive description updates, your node can run a bit into problem, because you see that CPU, okay, it increases like in other figures, but it increases already with 2.5 description changes per, actually what is it? This was per second, as I remember. I'm sorry that the dimension got lost here. But it's currently could be an easy attack if you launch nodes which are just frequently updating their description, or you just create a massive amount of dummy nodes that you just throw away afterwards just to stress others. This can be a problem that is a bit part of my future work. Okay, so the conclusion. I pointed to some requirements or some challenges for open and decentralized networks, and why I think it's hard to find to solve this problem, especially regarding finding consensus on who's trustable and who's not. I proposed a way to do it anyway, just by leaving this decision to the individuals, and validated it with my implementation, which showed to be feasible in embedded devices and up to a given number of nodes, which is also common for many existing community clouds. Many clouds are in the range of 100 or 200 nodes, and as we've seen, it could scale up to even more. At least it was not reaching the limit of these nodes yet. And what I want to do next is look a bit on denial of service attacks, how, for example, some creation of dummy nodes can be defended against, and what is already working experimentally is that you can import trust decisions or trust sets from others. So the idea is simple. In every community, there are often some activists which take care of socializing and bringing people together. As I know, most of the people, if they take the effort to, let's say, make a list of those they know and where they have the feeling they do a serious job with their setup, they are good candidates for maintaining such trust sets, and others can just dynamically import their decisions. It's still not centralized, because everybody is free to create such lists, and everybody is offering them automatically for others to import them. But it would, the benefit is that not everybody has to take care of this job if he's willing to delegate this decision finding. That's it. Thank you. Maybe if there are questions, proceed. Yeah.
So you are using Polar SSL for the asymmetric encryption?
Yeah, exactly.
Okay.
What does it mean to distrust the node? Do I still route traffic for untrusted nodes? I mean, I can still route traffic
If
for
I
them
distrust
if I
a node,
like.
that means I remove it from my trust set. It only means it's not allowed to route my traffic anymore. It doesn't affect any other node. Other nodes can keep it in their trust set, and traffic to this other node it will be routed potentially across this node where there's controversy above. So yeah, I think. Yeah, here we have an example. Here we have this green node, which trusts these X and these dollar nodes. So as a consequence, there is a path which can go all this way, right? Because there are physical links between these nodes, and these nodes are trusted by the green nodes. Let's say the X nodes only trust the other X nodes. So although the green traffic is allowed to cross via their infrastructure and via the links established between the X nodes, this end-to-end route between the green nodes does not affect these nodes. Because in the trust sets of these nodes, there will be only 4 entries, 1, 2, 3, 4. Like that. Yeah?
Yeah. What about taking advantage of routing information provided by untrusted but not certified enemy, but untrusted, unless it contradicts information from a trusted node?
You would like to do that?
Yeah.
You can write an application. Yeah. You can write an application which takes care of managing your trust set by learning from the trust sets of others. You know the trust sets of all other nodes. They can be completely different. And you can write something which is just analyzing these data and say, let's say, gives preferences or trust levels to some of them and ranks the decisions of them higher or than others or something like this. So, but as I said, it's outside of my protocol. You can control all these with some simple commands. The existing data can be exported with JSON and is easily parsable. And so you're free to do this. But I'm not considering this my job.
To sort my orientation out for these protocols, how would you classify this protocol to an application in GNU-net? So I do find in relation to the application, it's very similar. It has some effect or some possibilities which are given in GNU-net also. So to sort this out, it's a layer down there as a transportation layer or whatever helping, or it's literally the same, or it's very different, so can use one with the other. Help me with this orientation. Where I put, if I take this one, BMX7, and I have the other round GNU-net, how do I level this? So where do I find the same, it's not the same?
I think they cannot be so easily compared. They are working on different layers. They have also different, well, I mean, at least, oh yeah, maybe just.
I'd say BMX7 can compare with the routing layer, which is inside GNU-net, just like GNU-net, because it has all this naming system sitting on top and lots of transport systems sitting underneath, which are not necessarily IP based, while BMX7 obviously it's on top of IP interfaces. I'd say it's BMX7 is similar to the, layer-wise, it's the same place as the routing layer in GNU-net and has similar properties also by now. just like GNU-net has a lot of layers sitting on top which allow you to, for example, manage those trust sets and inherit trust sets or delegate trust sets from others, similar to how you would do it for the naming system.
I must say I'm often mix up a bit the concepts of CGDNS with GNU-net.
Yeah.
That's what makes it difficult for me to explain differences. But what I don't, if you have selective dropping, for example, or asking another way, can an individual in GNU-net say, I don't want my traffic routed across this potential device? Because I understand it's in the end a consensus decision driven by algorithms.
Yes, exactly.
And an individual cannot control that. If this particular device behaves mostly correctly and just casually drops or eavesdrops the traffic of another individual node, it will be hardly detected.
Right, it will be detected if the node drops traffic or maliciously
in a wireless
manipulates the
network,
traffic.
In a wireless network where you have packet losses anyway.
Yeah, but it doesn't matter if it's dropped on purpose or dropped on mistake. It's not a reliable node then if it drops.
So
and
any node in a mesh network is not reliable.
To a certain different degrees,
in a wireless network,
yeah, to a certain degree always, of course. There's no absolute reliability. And surely you need to define like some kind of threshold from which point on a node will be unreliable. In terms of eavesdropping, it doesn't really matter because everything is encapsulated and encrypted in a way that even the metadata is only known at the endpoint. So an eavesdropping node wouldn't have any advantage from eavesdropping that noise.
Depends how curious you are about DPI and this stuff. That you are, maybe you're not eavesdropping, but you do selective dropping on some certain amount of traffic just to make this connection a bit unusable or less unusable than somebody would expect.
Yeah, definitely. These are attack scenarios to be considered, I reckon.
But
I have a question myself.
Please.
Or did it answer your question?
Just proceed.
Similar to traffic, also trust is a not necessarily symmetric property. So now obviously both the green nodes in the example would trust all the X and $$ nodes, but let's have another color introduced. Let's say we have an orange node and it trusts only the X nodes, but also...
No, I completely understand your point.
So does that lead to asymmetric links that my outgoing traffic would take another route than the return traffic, or would it work the way connection tracking solves it?
The protocol doesn't try to find a consensus, let's say, between the X nodes.
That's the question.
It means, I use this, I simplified this a bit, like assuming these two nodes have exactly the same assumption of trust. But in the end, it will be, it could also happen that he wants to communicate with this node, okay? And then the traffic towards the green node will be routed according to the trust set of the green node, and on the reverse path, it will be routed according to the trust set of these $ nodes. One other thing that should be remarked maybe is it's only about the trust set only says who's allowed to route my traffic, not so relaying my traffic, not who's allowed to receive my traffic. In this sense, let's say these nodes don't trust each other. They could communicate because if the packet goes this way, the red node never, and the other way as well. Sorry. Let's say the green node can send traffic to the red node, although it doesn't trust it, for example, because the red node is not relaying traffic to the green node.
So I have two short, I hope, questions. One is if the node description is extensible, easily extensible. If the node description can be extended with other components.
If the node description can be easily extended. Yes. There are plugins which are using this. For example, the short message plugin where you can put any kind of string. There's also one which can be used to spread files, actually. So you just, in the configuration, you say the content of this file should be propagated, and the daemon monitors if the file changes, and once it changes, it propagates this over the network.
So you could also publish a list of untrusted nodes. So you can also publish a list that nodes...
You could do that. Personally, I don't believe in propagating something I don't trust. Because, I mean, if the guy who I distrust and I name him can just change his identity and it doesn't make sense anymore. But you can do that.
Yeah,
yes.
but it would be like, I want relay traffic for these guys, so don't send it to me. And the other nodes would just know that they cannot rely on you for their packets and go around you somehow.
Personally, I don't consider, if I'm not relaying traffic for somebody, I don't consider this an attack unless I'm saying so. In the end, it's like if I put a node or not. If I'm not putting a node, I'm not an attacker. I'm just doing nothing. I become an attacker by putting a node who's claiming I'm providing some service for you, and then I don't do it. Because then I give you some foolish information that you rely on.
Well, I'm thinking not of an attacker, but at the community network scenario. Like you might have some people that you like and some people that you don't like, and you just don't want to have their traffic through your node for some reason.
Yeah, but I mean, what you could easily do is just not propagate his routing updates. By not propagating his routing updates, they are not traveling across you, so no path to him will point across you. And that's some kind of valid approach. Of course, you can be exhausted for selfish things, but in this moment, you're not claiming that you're providing a service for him. So, and yeah.
Okay, thank you.
Are there any other questions?
And by the way, I want to mention Guido wants to spend some more words on BMX6 and integration, and I want to hand over to him before the time is over. But please, I think.
Also, just a comment from my side. And when I think of how to use this, for instance, in our community network, no? So it would end up in saying, okay, on our 100 nodes, even if I distribute the who trusts whom, and ends up 100 nodes are trusting each other. So I would somehow secure this routing thingy against, let's say, potentially new ones that need to ask somebody. Okay, that might be one case. And how quick can I, also let's assume I identified this guy is behaving wrongly and I want to exclude this node from the routing stuff. So I would just take out the don't trust this idea and fine. Yeah?
Yeah, well,
okay.
you don't put it in.
Yeah, yeah. Also,
yeah.
when I remove.
Yeah.